Hello students, quite after a long time we are meeting. I hope the schools might have opened in some places. I was too busy due to hectic schedule. I could not shoot videos. I am shooting on a Sunday today. Yes, I will try to shoot two videos a day and send you. By most probably the month of February, I will complete all the units with numericals and some examples from the previous year question papers. Thank you for your patience. Now, today we are going to continue with magnetic field due to a solenoid. Now, what is a solenoid? Solenoid is nothing but a wire. Okay, now I wind this wire in a form of a cylinder, right? See, like this, like this, like this, like this. Yes? Now, I wound it like this in the form of a cylinder. It is having circular things in it, and this is a solenoid. A solenoid is nothing but a straight wire. But what will happen in circuits, in electronic circuits, you cannot connect a long wire. It will occupy more space. So what we do, we make it into compact form. For compact form, we just make it in the form of a solenoid. A solenoid is nothing but a straight one which is being wound in a form of a cylinder in circular loops. Okay, circular loops with like a cylinder. It can have more number of turns. It can have n number of turns. It can have 500 number of turns. It can have 1000 number of turns. Usually it is copper. You can find it in fans, in motors, all you'll find solenoid being there. It is made up of basically copper. Now, I am going to take Ampere's circuital law. We studied, that is, the line integral of the magnetic field over a closed loop is equal to mu naught times I, where mu naught is a constant permeability in free space. And also we learnt about Biot-Savart's law. And now we moved from Biot-Savart's law to Ampere's circuital law. Now see what I am going to do. I am going to draw a solenoid. Yes. You see circular loops are there and it is in a cylindrical form. Yeah. This is a solenoid. What is our talk? When current is allowed to flow through. So let me connect it to a battery. Fine. And a current is allowed to flow through. A magnetic field is produced. We all know that in the case of a long straight wire, we said that if current is flowing in this direction, we very clearly stated if current is flowing in a conductor, then if current direction, conventional current is upward, then the curled fingers shows you the direction of the magnetic field. So again, let us recollect it. A wire is there, current is going like this. You'll find that they are all like concentric circles. Now it is going in this direction, so the magnetic field will be in anti-clockwise direction. Suppose if current is coming from top to bottom, again the same concentric circles will be there, but it is going to be now clockwise direction. The direction is going to now change. So this is going to be the direction. This is what we called as right hand thumb rule. Right hand thumb rule. Now we move on to a solenoid. In a solenoid, let us say the length of the solenoid is going to be L, let us suppose, length of the solenoid. And let us say it has n number of turns, capital, let me write somewhere else here, it has got n number of turns. Now current is flowing through, you see what is happening, current is flowing through in the loop, yes, and again it is going back in the other part of it like this, yes. Now what will happen actually, a magnetic field is produced around this solenoid. Yes. Now you will find that the magnetic field produced will be somewhat like this. Let me erase this. Diagram is more important. This will behave more or less like a bar magnet. You see, magnetic field is produced. A magnetic field is produced. Again, magnetic field is produced. Yes, two lines will never cross each other. Again, magnetic field is produced. Yes, magnetic field is produced. First, to find out what is the magnetic field. Okay, now we are going to use Ampere's circuital law. Fine, we are using Ampere's circuital law. We wanted to find the magnetic field. Keep the magnetic field here. Integral dl is equal to mu naught into I. But I said to you, it is having n number of turns. This is number of turns in the coil. So the formula will become B integral dl is equal to n times mu naught I for n turns. For n turns, the rule will be like this. Okay, now that is B into, what is integral dl? Total summation of the length of the whole loop when you take it, that we said L, that is equal to n mu naught upon I. And if I say B is equal to n upon L, close the bracket, mu naught into I. Now what is this? Number of turns per unit length, that is called n number of turns, number density or number unit length. Number of turns per unit length, that is n upon L, can be written as small n, and this is usually given to you because the length of the solenoid might be more. Here I am taking a thick wire and a big wire. So for you it looks like this. Suppose if I take thin copper wires and make it so many turns, then I can only say that total number of turns is 1000 and the length it is lying is 2 centimeter. Then we can find out number of turns per unit length, that is small n. So the standard is to represent this as small n and mu naught into I. So what is the magnetic field due to a solenoid? B is equal to n mu naught into I, and this is the formula. I hope you understand. This is very simple derivation. Now when you come over here, it is fine. In the middle it is fine. You see here, everywhere it is fine, but at the edges you will find that the value will drop to half its original value. Why? Why the formula will be mu is equal to n mu naught I divided by 2 at edges. What is the reason for that? We should know that. The reason is, when I take a loop like this, a solenoid like this, if I take a loop in the middle here, it is supported by one in the right and one in the left. So there is a total magnetic field. But when I take one at the edge here, the magnetic field is due to only this here. And what about this side? There is nothing. That is why the value drops to half value. Now, for example, if I take here, in the right there is a loop and in the left there is no loop. So the middle one which is going to be is affected by only the right hand loop, and left hand there is no loop. So for the whole solenoid, at the center middle part, the magnetic field will be very strong, and that is n mu naught I, where n is equal to n upon L, that is capital N upon L, total number of turns per unit length, and at the edges it will drop to half its value. Yes, and this is the magnitude part of it. Now I wanted to proceed with another idea. Whenever you say there is a magnet is having north pole and south pole, and where is the north pole and south pole in a solenoid, in a long solenoid, in a straight solenoid? We have to find out. That is very simple. It is reverse of the one which we did right hand thumb rule. Here what you do, you hold the solenoid with your curled fingers, curl the fingers, and the thumb will point towards the direction of north. Actually, here I have written capital N. This I can modify into this is north pole. Yes, and naturally, if one is north pole, the other will be ultimately south pole. You need not worry, right? What we have to do, we have to take the solenoid, yes, and current is flowing through the solenoid, right? It is flowing like this, and I will hold it like this, right? And curled fingers shows me the direction of the current, and this will give me the magnetic field. The thumb will give me the magnetic field direction. Or the magnetic field polarity is north, and ultimately the other end will be south. I wanted to tell you something, right? And this bar magnet, it's like a solenoid is behaving like a bar magnet. Don't think inside there's a bar magnet. Okay, I'm just telling you an example. Here, this is north pole and this is going to be the south pole. Fine, it behaves. The solenoid behaves like a bar magnet. Yes, this is the magnetic effect of current. This is one of the first and foremost derivation I have done today. Now, this rule you can also apply in another way and understand in more easily. There is always certain times you have clues. Okay, we can use those clues and we can identify certain things now. Okay, I know the solenoid is made up of circular loops. Yes. Now I wanted to say this is north pole, and you see what I am doing? This like this like this. Okay, now I cross it like this. North. What is this? N. Am I right? It looks to you something like N. And you put an arrow mark over here and put an arrow mark over here like this at the two ends. Now you see, and this is the direction of the current. If the direction of the current is anti-clockwise, then the pole will be north pole. Very simple, right? This is also called clock rule. This is called clock rule. Let me take one more example. Again, for south pole, what is going to happen? Now, you see, now I will just draw something, yes, up here, and down here, right? And I will connect it like this, right? It looks like S now, you see? It looks like S now. Yes. Now put an arrow mark at the edges, at the tips, right? Now you see here, and it goes back like this. And this is not the clockwise direction. So clockwise direction, if the current is flowing through, then that will be south pole. It will represent the south pole. This will come to you by practice. More you keep the wire and do some numericals, you will be able to do it. Now let me proceed from here to the next concept called toroidal solenoid. Toroidal solenoid. Okay. Now let me take the ampere circuital law as it is. Integral B dl over a closed loop is equal to mu naught times I. This is done. This is ampere circuital law. Yes. I got a long solenoid, a straight solenoid, and let me erase this now. Okay. This part is over now. We have to derive an equation for a toroidal solenoid. What is this? Looking very horrible word. Toroid. Toroidal. Okay. How is a toroidal solenoid? It's very simple. Yes. Let me make a solenoid first. Wire is there. Let me make a solenoid first. Okay. I'm making a solenoid. Basically, you need a, let us say, cylindrical object. It will be easy to make it. Yes, I made it. Now I stretch it like this in circular form. I stretch it in a circular form. You see what I am doing? I take a circle to draw, yes, and I am going to take two lines here, okay, and I am going to make the loops like this. And this is called a toroidal solenoid. Same straight solenoid. It was really a solenoid like this. And what I did, I just turned it and made it in the circular form. And this is called a toroidal solenoid. When it is in a circular form, naturally it is supposed to have a radius. Okay. Now the whole thing, we are going to derive what will be the magnetic field inside the loop, inside the toroidal solenoid. That's what we are going to now calculate. The magnetic field intensity will be very strong inside. Okay, now we got the formula, ampere circuital law. So B into integral dl is equal to mu naught into I. But when you have n turns, for n turns, the formula will become n times mu naught I. Okay, now that is B into integral dl. Integral dl is total length of the solenoid. Instead of putting L, I have to put, it is in circular form, circumference of the solenoid. That is 2 pi r, which is equal to n mu naught I. Or I can say B is equal to n mu naught I upon 2 pi r. So this is the formula for a toroidal solenoid. It is very simple. If I convert the same thing, 2 pi r to be the length, then what will happen? N mu naught I is equal divided by length of the solenoid, right? And that is n upon L. Number of turns per unit length, that is called small n, n mu naught I. Ultimately, the formula is same, n mu naught into I. Whether if it is a long solenoid, you just put only the length, and if it is a circular form, you can apply that of the circumference of the circle you have taken. I hope you understand. These are the basic ideas in the first part of it. And next we will move further, taking the force acting due to the magnetic field, and that will be the next video. Thank you so much.